Hello everyone. So let's begin, please. Uh, let's also wait 10 seconds. So be 12:16. So it's fine. Please click on yes for present. So let's begin our lecture. So what we have seen before, we started already basis and dimension. We have seen what's meaning of basis. I guess have you seen the wiki assessment 4? It's already on Moodle. Okay, very good. So today's lecture is nothing to see with, or if you want, yes, no problem. So we have seen basis and dimension, and we have seen that the dimension of Pn, what does mean? Pn means polynomial with degree maximum equal to n, and in addition to this one is 0 degree because the zero polynomial is because degree. And we have seen the standard basis or the natural basis. So we say natural or standard. What's the standard basis for Pn? Standard basis is so we start with the maximum degree, it's t to the power of n, n minus 1, and to arrive at the end to t squared t and 1. For example, what's the standard basis for P2? We say for, not of. For P2 is t squared t and 1. Like here, basis 4. And what's the standard basis for P3? Is t cubed t squared t and 1. Okay guys, this one we have seen it before. And even we have seen the natural basis or standard basis. So we say standard or natural. For Rn, so Rn is vector with n components. For the first vector, we take it first component equal 1, other 0. Second one, we take second component 1, other 0. And so on. Last one, last component equal 1 and other 0. Okay guys? Now we will study subspace. What do we know about subspace? Subspace itself is a vector space. So we can find also basis for subspace is exercise 19 from the textbook. So find the basis for the following subspace W of R3 consisting of all vectors of the form ABC such that B equal to A plus C. It's very easy, guys. Today's lecture is very, very fast and very easy. So here, first we have to find a set which is spanning and linearly independent, correct? To find the basis. So we have to pick a set which is spanning plus linearly independent. Correct, guys? Here I don't have any set. I have only the form of W, which is the set of all vectors of the form ABC such that B equal to A plus C. Isn't it? So what's the form here? Instead of B, we will put A plus C. So the form, what's the form of any vector in W is A, instead of B, we put A plus C and C. Correct, guys? Now, how many parameters do we have inside this general form? Two, A and C. Parameters, A and C. We don't have three. Of A, C, C. So A and C. So let's separate it as two vectors. The first one we put only A, and here we put only C. So here, for the first row, how many A do we have? We have one A. Here we have one A. Here we have 0. Here, C. How many C do we have? 0. How many C? 1. How many C? 1. So if we take A common factor here, A is multiplied by what? If you put A outside, you will get 1, 1, 0. And C, what do you get? Tell me directly the vector. Mira already correct, yeah. So 0, very good. So look guys, any vector is a linear combination of V1 and V2. What does it mean this one? By definition, if any vector is a linear combination, so what can we say about this set V1, V2? Spans W. Because here we take any vector is a linear combination, so it's span. This is the definition of span, correct? Is it clear for all of you guys for the moment? Because once you understand span class, you prove it's linearly independent, basis finish. Okay. So this is how to prove its span. Yes, so you take any vector, you split it, you have two parameters, you split it in first parameter, second parameter. Clear, Hamad, so far? Then, here if you put A outside, you will get 1, 1, and 0, like common factor. If you put here C outside, 0, 1, 1, correct? So look what we have. We have any vector u is equal to a v1 plus c v2. This is the definition of span. Remember span? So v1, v2 span w. This is what we said here. Okay. Now let's check if it's linearly independent. So definition a1 v1 plus a2 v2 equals 0. We write the augmented matrix 1 1 0 0 1 1 and all 0. Now we have VB1, we cancel everything below it, up to minus R1, 1 0 0 0 1 0, and the last row we didn't touch it. Now second 0 is 1, we cancel everything below it, R3 minus R2, 1 0 0 0 1 0. So how many variables do we have? We have A1 and A2. And how many leading ones do we have? So each variable has leading one. So how many solutions do we have? Yes, we have trivial, because here it's homogeneous, trivial solution. So what does mean this one? Means V1, V2 are linearly independent. So guys, look what we have. 1, 2, 1 and 2 gives what? Conclusion. We have span plus linearly independent. What do we get? V1, V2 is a basis, very good. For what? W, don't forget, not R3, because R3 we need 3 vectors. False. For W, because for R3 we need 3, but here we are finding basis for W. Now tell me, what's the dimension of W? We know dimension of R3 is 3. Dimension of R3 is 3, but dimension of W, it's the number of vectors in the basis. How many? 2. So that's different than R3. If dimension equals 3, then it's equal to R3. But since the dimension is less than 3, so it's different. Is it clear, guys? Count, Nora. How many vectors here do we have? What's the meaning of dimension? Means the number of vectors of a basis. Okay, Hamad? Please take a screenshot. Okay, so we have another one. Same. Subspace W. Yes, right. Even for others, guys, you cannot hear me well? Okay, let me try another thing.
You are currently the only person in this conference.
Raghat? You need to reconnect. Guys, please write if you can me. Okay, okay, very good. Okay, very good. So here again, guys, we have subspace W. The form is ABC such that 2A plus B minus C equals 0. So here we can write one variable in terms of others. So which one? Let's move C to the other side. What do we get? C equal how much? 2a plus b. Very good. C 2a plus b. Very good. So what's the form of any vector in W is, instead of C, put 2a plus b. So a, b, instead of C, 2a plus b, correct? Now split it into how many? Two vectors again. Here, put only a. So what should we put? Tell me here, what should we put? Not a1, yeah, but so it's a, 0, no, 2a, plus b, so 0, b, and b. Pay attention here, we have 2a, Abdullah. So we get a, if we take common factor, you see Hamad, take common factor, what do we get? We get 1, 0, 2. Plus b, 0, 1, 1. Very good. So here we have v1, we have v2, so same. So v1, v2 spans W. Now let's check linear independence. A1 V1 plus A2 V2 equals 0. So the augmented matrix 1, 0, 2, 0, 1, 1, and here all zeros. So I have leading 1 here, 0. To make this one 0, R3 minus 2 R1. 1, 0, 0, 0, 1, 0, and minus 2 plus 2, 0, 0, and 1, 1. Leading 1, so R3 minus R2. It's similar, a little bit similar to the previous one. Correct? We get almost the same result. 0, 1, 0, and all zeros. Again, how many columns here? We have 1, 2, and each column has leading 1. Here 0 equals 0 for sure because it's homogeneous. So we have unique, trivial solution. So is it linearly dependent or independent? Very good. Is linearly independent. Conclusion. One does not span. What we have seen before, remember we had vectors that is not spanning. We have already examples for if you go back to 3.4. Okay. So conclusion. But here for subspace, always you will find span because you are splitting the vector. So by definition, spanning. So conclusion, V1, V2, very good. Is bases. And what's the dimension of W? Very good. Very good. Please take screenshot. I will erase and I will show you what's meaning of this one. What's meaning dimension 2 and its bases in and we are working in the vector. The biggest vector space here is R3. Okay. I will erase, okay? So this one is here. So we have seen that V1, V2 is bases. So basically, if we plot R3, what's meaning R3 means you have X, Y, Z. Correct? This is R3. Now I have subspace W, which what's the basis of subspace is 1, 0, 2. So here if I go 1, 0, 2, so 1, here 1, 2. This is V1. And V2 is 0, 1, 1. So X, don't move X, move 1 and 1. And this is V2. So look, the plane passing through these two vectors, we have only one plane, this one. This is W. So you see W. Like paper. Paper is, what's the dimension of a paper? How many dimension we have in a paper? It's 2. Look, W is 2. Like screen in front of you, the screen is 2D, right? But the word in front of you, when you see with your eyes, it's 3D. So here, look, W is this plane. The basis means, look, with two vectors, you can form only one plane, which is this one, okay? So this is how to know W. And look, dimension is 2, it's logic. Understood, guys? So W is a plane in R3, too simply. Okay. You like it? Now, let's continue. We are almost done, guys. Remember this one, we did important fact. If we have k vectors in Rn, if k is bigger, strictly bigger than n, then directly v1, v2, vk is linearly dependent. This one we did it. Now, if k equal n, then you find determinant of A. If determinant of A is equal to 0, means it's linearly dependent. Different than 0 means independent, right? We did it before, this one. If k is less than n, we have less number of vectors strictly less than n. What's n? What's the meaning of n? Means the power of r to the power of n. This n, we are talking about this n. So if number of vectors is less than n, strictly less than n, then you have to use definition. So you write the augmented matrix and you see if you have unique solution means independent, infinitely many solutions means dependent. Clear? This one, we have seen this one before. Now, for bases, if dimension of V is equal to n, we are not talking about Rn, we are talking about any vector space. And we have n vectors, so k equal n. For bases, guys, if k equal n, then you see if it's a basis or not. If k is different than n, directly through it, say it's not basis. If k is different than n, then for sure it's not basis. Okay, guys? Always. Very good. So, and if k equal n, look, this is very important. To prove it's a basis, it's enough only to prove it's linearly independent or span. And usually, linearly independent is the easiest one. So, from now on, guys, if you want to prove it's a basis, you have to say that k equal n. So it's enough to prove only linearly independent, because if k equal n, basis is similar to linearly independent and it's similar to span. What's the meaning of this one? An example. Look, guys, how many vectors do we have here? K equals 3. And what's the dimension of the vector space here? The vector space is R3. 3. So k equal n. So look, to check whether V1, V2, V3 is a basis, it's enough to prove, it's enough to check that no need for span. V1, V2, V3 is linearly independent. It's enough because K equal N. Okay, guys? Clear? Always. In fact, always. If K equal N, directly only do linearly independent, forget about span. Because K equal N. If K is different than N, directly it's not basis. No need to do anything. What do you mean if no, we check span? No. If K is different than N, directly it's not basis. I'm talking here only about basis. If you want to check basis, no need anymore to do span and linearly independent. One is enough. And usually we check linearly independent because it's easier. Here, since K is equal to N, we can directly do determinant. V1, V2, V3 equal to 1, 2, 3, 0, negative 1, 2, 0, 0, 1. What's the determinant of this matrix? It's lower triangular matrix. So we multiply the entries of the main diagonal. 1, negative 1, 1. We get minus 1 different than 0. So is linearly independent. Correct? And conclusion. So you see, no need, خلاص. No need for span. V1, V2, V3 is the basis for R3. Look, if we get here 0, if we get 3 vectors determined equal 0, directly it's linearly dependent, means it's not basis. Okay? Because they are equivalent. And you see here dimension is 3, which is correct. Because we know already, look, it's here. No, because it's W. You don't know what's the dimension of W. W, you don't know it. But R3, you know dimension of R3. Before, you don't know what's the dimension of W. You don't know, right? At the end, we know it because we get the basis. But if we don't have, how can you know what's the dimension of W? It can be 1, it can be 3. So you don't know. Clear? Okay. Important fact means, yes, if K equal N, always, if you know dimension, look, if you know dimension of the vector and K equal N, you can use it directly. Okay? Now, the last one. Look, guys, how many vectors do we have? And dimension. So it's different. Okay, different than N. So immediately V1, V2, V3, V4, what is not a basis. Clear, guys? Look, for example, if we go back to the previous lecture on Monday and Tuesday, here, we took this example, V1, V2, V3, and we proved its basis. We did span plus linearly independent. But now, let's redo it. K, 3, and dimension K equal N. So it's enough only to do, it's enough to check that V1, V2, V3 is linearly independent. Okay, so we take V1, V2, V3, 1, 0, 1, 0, 1, negative 1, 0, 2, 2. So we have plus, minus, plus, minus, plus, minus, plus, minus, plus. So we take the first row, for example, yeah, because we have two zeros. We take the first row, 1, we don't change the sign of 1, change the sign of 0, but we don't care, and we don't change the sign of the last 0, but we don't care. So for 1, we don't change the sign. 1 multiply, hide 1, hide 1. So we get 1, 2 minus 1, 2. So you see, it's very fast. So we get 2 plus 2, 4, different than 0. V3 is linearly independent. Directly, no need for span. Conclusion. Already look, we said k equal to 3, n equal to 3, k equal n, and we need only linearly independent. So already we justify our answer. So conclusion, V1, V2, V3 is basis for R3. Understood, guys? You understand the important fact, guys? Very good. Let's do, for example, this exercise. We have P1, P2, P3 is basis. We have how many polynomials? How many? Look, we have 1, 2, 3. And dimension of P2, how much? Oh, P, it's 2 plus 1. Dimension of Pn, okay, we start with this one. Dimension of Pn is n plus 1. So dimension of P2, 2 plus 1 means 3. Pay attention. So we have k equal n. Again, it's enough to prove only linearly independent. Can we use determinant here? No, because we don't have Rn, so we have to use A1 P1 of t plus A2 P2 of t, A3 P3 of t, very good, equals 0. But we can write the augmented matrix easily. So here t squared, t and 1, we don't have t, so 1, 0, 1. Yeah, very good. 0, 1, minus 1, and we did it already. So here 1, here 1, R3 minus R1. Minus 1 plus 1, 0, minus 1, 2, 0. And R3 plus R2, 1, 0, 0, 0, 0, 1, 1, 0. 0, 0, 3, 0, and the last step is R3 divided by 3. 1, 0, 0, 0, 1, 1, 0, 0, 1, and 0. So we have leading 1 per column. Each column has leading 1. So unique trivial solution. And P1 of t, P2 of t, P3 of t is linearly independent. And what's the conclusion? No need for span. Remember before we did it with span, but now we know if k equal n, just do one of them, linearly independent or span. Conclusion. What's the conclusion, guys? Is basis very good for P2. Understood? Very good. Guys, so we are done with chapter 3. This is everything about chapter 3. I think we will stop here. And now I will receive your questions if you have any. So we are done. So now we know everything about bases. You can hear me, right? So we know everything about bases, about dimension, how to prove bases. If k equal n, directly do only linearly independent, no need for span. Or you do span, no need for linearly independent as you wish. And if k is different than n, it's not basis. However, for span, you have to do, if only span, if I ask only span, you have to do definition. If I ask only linearly independent, you use definition or determinant, but always you have to justify your answer. And don't forget, determinant, use it only for Rn, not for P, not for polynomials. That's it. If you don't have any questions, thank you very much. And if you have questions, please feel free and ask me. Have a nice weekend. Thank you, Abdullah, and all of you. Thank you all.